Hi, I just wanted to give some feedback on the core test that we wrote in class. On the whole, there's certainly some main sections where everyone is doing really well at, and so that's fantastic. So for instance, these first questions, identifying lone pairs, charges, the molecular formula, we've done very well. Identifying these functional groups as well, ether, amine, secondary amine, done well. Being able to draw out something like para-isopropyl fantastic as well. And then just the solvents, dichloromethane and tetrahydrofuran, who also answered very well. So on the whole, the class did exceedingly well on the first page. On this page over here, it became a little bit more tricky, but generally people got these two questions, identifying the nucleophilic and electrophilic parts of the molecules, down very well. And if you didn't get that right, I encourage you to speak to someone who did get that, and you can have a look at what they got, and you can look at that. Also, stereochemistry, drawing out an enantiomer and a diastereomer, almost everyone got that correct, so that's fantastic. The problem really came up with the mechanism that was here. And what I've done over here is, and I want to just talk a little bit about it because I think it really is important that we make sure that we understand how to do these mechanisms and what the classic mistakes are to watch out for when you're doing a mechanism like this. So what I've done here is I've drawn some arrows which were extremely typical from within the class and very normal, if I had to be honest, for many of the answers that were coming up. And I want to show where the problems are. So I think it's good to look at something that is wrong, and then we can discuss how we actually do this to make it right. Now, first of all, there's only 3 blocks where you have to draw out any kind of mechanism arrow. And I want to just look just generally at this sort of thing over here. So we've got an arrow going over there towards the aluminium, and we've got an arrow breaking this carbon-chlorine bond going onto the oxygen. Now, the first thing that should stand out for any mechanisms is the minute you have arrows that are going off in opposite directions. You can see these 2 arrows are basically starting next door to each other, and they're heading off in opposite directions. The minute that happens, it's wrong. It cannot be right. There's an incorrect flow of electrons. So when we look at the second option over here, there we can see kind of there's a flow of electrons. This is also wrong. We'll get to that now, but there is a flow of electrons. So that immediate sense of, something is completely wrong is not there because we've got the arrows going in the same direction. But here in this question over here, you see exactly the same problem again. You see how this arrow is going this way. This one is heading off in this direction. They're kind of coming together. And that's already a sure sign that something is horribly wrong there. So let's go back and just look at what was happening over here, perhaps in the way that this person wrote it out. I don't know who it is, but as I said, representative of many, many people. First of all, when we look at the way to do the mechanism, we need to look at what we're heading towards. And over here, we've got 3 chlorines of the aluminium, and here we've got 4. So this chlorine has connected to that aluminium. There's a new sigma bond that's been formed. One of those is new. They're all the same, but one of them is new. And so we have to think about, well, how would that sigma bond form? Now, some people thought that the aluminium has a lone pair of electrons, which you can donate to chlorine to pick it up. So what they would do is they would draw this going towards this chlorine, and then, of course, this bond has to break, and they'd show it going in this direction over there. So there are a number of ways of analyzing this problem. The first thing is, well, aluminium doesn't have a lone pair. And if you go and look at your periodic table, it's below boron. It's one of those metals that actually has an empty p orbital. Maybe you've forgotten that, and that's okay. But what I would hope you haven't forgotten, though, is that aluminium, like all metals, tends to be a Lewis acid. In other words, it wants to accept electrons. That's why it's important to be able to identify Lewis acids and Lewis bases, which is kind of what this question was also asking you to do. And so then the idea that we've got lone pairs of electrons on this chlorine being added to the aluminium like that sounds really good, because if you're adding electrons to aluminium, the whole thing is going to become negatively charged over there. So that makes sense over there. Why does this arrow not make sense, and what should it be? Well, if we take electrons, all right, from this sigma bond over here, and we move them up. And now the thinking, of course, is that we want to form a triple bond to oxygen, and he has a double bond. So the idea is, well, this bond has to break. So the student kind of recognized, okay, that's got to break. But I want to break it so that I can make a triple bond to the oxygen. Now, the problem, of course, is that if you know your lone pairs, the oxygen is sitting with two lone pairs, and there's two electrons each that are sharing those bonds. So the oxygen has its octet. It's got 8 electrons around it. It cannot accept any more electrons. If we added more electrons to the oxygen, it would actually be negatively charged, not positively charged like that. And so this is the problem with this arrow over here. So the first instinct was the arrows going off in the opposite directions. There's a problem. The next one is to recognize that this movement over here does not actually give this. This movement of electrons breaking this sigma bond, which has to be broken, is going to end up with the oxygen being negatively charged and also having 10 electrons around it, which it can't have. And so that's the problem with that one. We'll come to fixing it now. Let's just move on to some of the other problems. So in this step over here, we recognize that the trichloroaluminium, all right, has stayed the same in both, so we don't have to worry about that. But we have formed these two components, all right, and we've introduced this new one from before, this phenol, have been coupled to each other. Now, again, this movement of electrons that we're showing over here, it looks good because there's that flow of electrons. But when we analyze what's actually happening with those electrons, we have the same problem that we had over here. And that is that this pi bond, if we show it breaking to form a double bond there, and I know the instinct is we want to form the double bond. It's like, we can do some resonance, so we can move it across like that. But the problem is that if we move those electrons in like that, then the oxygen, which currently has 2 bonds and 2 pairs of lone pairs, is now actually going to end up with 10 electrons around it. It has accepted electrons, and if it's done that, it cannot be negative like that. Positive like that, it's going to be negative. And then the other problem is, of course, so this is a pi bond that's showing the electrons being taken away from this oxygen and donated to this carbon over there. By taking electrons away from an oxygen, which is positively charged, means that it's going to be doubly positively charged. So hopefully you can see that. If we take those electrons away, the oxygen, which is currently positively charged because it has a lone pair, all right, any oxygen with a positive charge has 1 lone pair on it, like hydronium, and 3 bonds to it. And so it's got 1, 2, 3, 4, 5. It only has 5 electrons, so it's positively charged because it actually wants to own 6. But if you take those 2 electrons and take them away to make a new sigma bond, which is this one over here that was formed between that carbon and that carbon and this carbon over there, if you take that away from that oxygen, it's actually going to end up with far too few electrons around it. It'll only own 6 around it. And of that, there'll be 6 electrons around, and of that, only 4 it'll own. So it'll be 2+. So this movement of electrons cannot be right. And then lastly, this one over here has the same sort of problem that we're showing over here. Do you see this common mistake? Is a recognition that we wanted to go from a double bond oxygen to a single bond oxygen, and we've moved those electrons away from the oxygen, so the oxygen is now going to be 2+. And that already shows a bit of a problem there. Now, it turns out this part of the arrow over here is actually quite good. It's correct. But let's go back, and I want to show you from first principles now how I would do a question like this and thinking about just how mechanisms work out. So how do I approach a question like this? What is the thing that I'm thinking about? Now, a question like this, I know for many of you, because I could see that the class was struggling with this, I know for many of you this feels really, really difficult. But what I want to show you is that actually when we are forming a bond, which is 2 electrons, when we are forming a bond, the electrons really have just one of 2 directions that they can move. And you always just need to choose the right direction. But if you think about it, it'll actually be quite easy. So if I look at this over here, now I know this mechanism, and I know how to kind of describe it in the way that it would actually happen. But we're looking at this mechanism having not seen this before. So now we're thinking about it in a much more kind of binary fashion. We're just trying to figure out where a bond ended up. And one of the first things that we noticed, and we've mentioned already, is that an extra chlorine ended up with the aluminium. And if you know that aluminium is a Lewis acid, and you see that we formed a bond to a chlorine, this chlorine must have ended up over there. Now, the chlorine has 3 lone pairs, and we've got 2 options here. So we're going to form a sigma bond between chlorine and aluminium. The option is either aluminium is going to donate electrons to chlorine, or chlorine is going to donate electrons to aluminium. Because aluminium has no electrons to give to it, it's a Lewis acid, what it wants to do is actually take one of those lone pairs to it. So the movement like that arrow, all right, shows the formation of a sigma bond from there to there. But we're not finished, of course, because in doing that, we haven't shown how this bond breaks over here. There is a sigma bond between this carbon and chlorine, and it's gone. There's the same carbon. It's now gone. 1, 2, 3. It's carbon number 3 over there. We should number it the other way, but don't worry. 1, 2, 3. 1, 2, 3. There's that carbon over there. It's lost this sigma bond. So this bond has to break. So the electrons are going to start in that bond over there, and they've got to go one of 2 directions. They're either going to go to this carbon over there, or they're going to go to the chlorine over there. Now, what's going to happen? How do we know where those electrons are going to end up? Well, if we take those electrons and put it onto this carbon over there, that carbon is going to be negatively charged. That we don't see. All right, that's nothing that we see over there. If we end up and take the chlorine, the electrons onto this chlorine over there, then the chlorine is going to be negatively charged. That's what we see over here. All right, this whole system over here is negatively charged because there's an extra set of electrons. So this bond has to have broken by putting its electrons onto the chlorine like that. All right, there's only that way that it could have moved. If you don't see that, I recommend that you draw this out in its full Lewis structure, show all its electrons, and look at what happens if you had to break and take those electrons, put them on the carbon, and only leave this with 6 electrons going over there to the aluminium. You're going to see it's not going to work. The right number of electrons won't actually work there. But of course, we haven't completed everything. We've shown now this sigma bond breaking, so that's good. We've shown it forming a new one to aluminium. It's broken between the carbon, but we have a triple bond over here. And how do we form a triple bond? Well, somehow we must get some more electrons into there. And the only way that we can do it is from the lone pairs on the oxygen over there. We've taken electrons away from this one over here. So that actually means that this carbon, if we've taken those electrons away, is now positively charged and the oxygen will be neutral. This is just a resonance structure. These lone pairs have to move in to form the extra pi bond. So we get the triple bond over there, and the positive charge will end up on the oxygen because the oxygen is now deficient. It's kind of given its electrons to stabilize that positive charge that's happened. When we look at this mechanism now, we worked it out back to front. Once you learn this mechanism for real, you'll actually go more from kind of like showing that this process is driven by these lone pair of electrons helping to kick in, and you see that movement of electrons. You see it's all going in one direction, and so it's very good. This one over here, we now need to make the same types of questions and answers we need to look at. So first of all, the aluminium tetrachloride is not involved, so we don't have to worry about that. All we need to do is we need to figure out how this and this connected to each other. The first thing is to what connected with what. So we recognize that this carbon is this one, and that carbon over there is that one over there. So somehow this carbon became nucleophilic and added to this carbon over there. And how did that happen? Well, there was also some other things that happened, and that's this pi bond over here has disappeared. It's now a single bond. And we've also got a single bond over there, which has now become a double bond over there. So how did this happen? So in the previous example, we saw that the student had said that the pi bond donates electrons over there, but that's where we can start with, because we can say, look, somehow we've got to get electrons. The electrons have to come from something. Those two carbons have no lone pairs on them. There's no lone pair or negative charge that can donate electrons one way or the other. So it must be coming from a pi bond, either this pi bond over here, which has electrons, or this pi bond. So there's two options. So the one is to take the pi bond over there and add it there. And we've already discussed that the problem with that is that if we take electrons away from this oxygen, it's going to be doubly positive. What we really want to happen to get it back to neutral, which is supposed to be over there, is that this pi bond, when it breaks, it has to break going up onto the oxygen like that. It can't break in any other way, making this carbon over there positively charged. It's the delocalization or resonance structure of that. So then how do we form the sigma bond? We don't have a lone pair or a negative charge there, but it's okay. We can use this pi bond, and the pi bond can donate its electrons over there, not the other way around, because if it adds its electrons over there to it, it's going to form that sigma bond like that, and we're going to be left with a positive charge over here. But that positive charge, all right, to get this double bond over here, we just need to move those electrons in like that. And if we move them in like that, what we see is those lone pairs move in, form the double bond. That will then move onto there and will break that pi bond like that over there. All right. And there we see this flow of electrons going in one direction. We don't have them going in opposite directions. Again, I want you to look at what you have done, and I want you to think very carefully about where you particularly went wrong, but also how all those little atoms all added up to each other, particularly the electrons, in the Lewis structures. And you'll see why this is the only thing that can work to go from there to there. All right. Now, I just want to make a point. I was okay if someone drew out, because you're working it out for the first time, you've never seen this. I was okay if you just show that arrow moved to make the double bond over there. That's good. You showed the pi bond breaking by giving its electrons onto this carbon in one step. And then in a second step, you showed the arrow of this carbon then adding to that one over there. I'm okay, even though conventionally we would draw it with one arrow. This is how we would draw it. If you worked it out step by step, and it's the same for this one over here, I accepted some step-by-step drawings there, that's okay, but it's that things are moving in the right direction. That's what I was looking for, and what is the most critical thing. So in this question over here, this last bit of it, what's going to happen? So we can see that aluminium now loses a chlorine. We're forming HCl, so H is bonded to Cl, so one of those Cl's is going to bond to H. I've drawn in this H over here. It was hidden, it was drawn there, but it's appeared now. And we can see that we've kind of formed the benzene ring again, so somehow a double bond is formed here, and this double bond has disappeared. Right, so aluminium is now neutral, and the chlorine has somehow picked up. So now we have to decide one of these bonds has to break, right? And we can choose any one. They're all exactly the same. One of them has to break. So where do the electrons end up on? So do the electrons go from here to there, or do they go from there to the chlorine? Well, the chlorine is the more electronegative. You're not going to end up on the aluminium, because the aluminium will end up being negatively charged and the chlorine will end up being positively charged. So they can only go onto the chlorine. So you're going to break that sigma bond. That's the only way that sigma bond could break. And once that chlorine breaks off, we're going to have, there's a whole bunch of, right? There's going to be 4 lone pairs around that chlorine. That chlorine now needs to connect to the H. So it can't, this H cannot give, if we're going to form a sigma bond between this chlorine and this H over here, the H has no electrons to give to chlorine. And if it had electrons to give to chlorine, all right, if you had electrons, just imagine, there's none, but let's imagine that you thought that, then if it had electrons, maybe you were taken from this bond, and you gave it to chlorine, chlorine already has 8 electrons around it. It can't take another one. So that and if it took more electrons, the whole thing, HCl, that would form would actually be negatively charged. But it's a neutral species. So the only thing that can be happening is that the lone pair is acting as a nucleophile and bonding to that H over there. It has to. It's the only option that could be occurring. But in doing that, this sigma bond must break. All right? That H is no longer, it's part of HCl over here. It is no longer part of this H carbon bond. So that needs to break. And again, we have to think about it. How is it going to break? There's only two options. Either the electrons are going to end up on the H or end up on the carbon over there. And hopefully you can see, well, it cannot end up on the H. For starters, we're going in the opposite direction. But the H would then have an extra electrons on, and the whole thing would be negative. So these electrons have to move onto this carbon over here. So I wouldn't draw the mechanism like this, but I'm happy if we end up with that. So it ends up putting the electrons on this carbon over there. But of course, that's not what we have here, right? I mean, there's no negative charge on this carbon over here. There's a double bond. But the negative charge that's on there actually can go in and form the pi bond over there. It's a lone pair, remember that negative charge. So it can go in and form the pi bond there because this double bond can break onto the oxygen like that. Again, for the same reason, just watch out for this. This is a very common theme and a mistake that I was seeing in the mechanisms, is that when you've got a positively charged oxygen, when bonds break, they always break towards the oxygen. All right, the oxygen wants to, it's positively charged. It wants to accept electrons. So it's always going to accept it. So we see it there. We see it there. Okay. So just watch that, that movement. Now, I would have accepted an answer like this. I'm happy for you to have worked it out piecemeal by that, and I wouldn't have marked you incorrect. But what we would have done for a real mechanism is we would have shown this bond just immediately forming a pi bond like that over there. That's how we would normally do that, because that's just taking in one step, and it's absolutely fine. That's a type of elimination reaction which we're going to do later on. So that's one way of doing that. Okay. Now, just to finish off, there were this is the only other problem question that I had. The abbreviations was done very well. So well done again on that. But this question over here, which I warned you about when I was teaching acids and bases, I said that this type of question would come up over and over again. And the numbers that I've written over there are not my numbers. These are the numbers of a student who did this. And this is a very common mistake again. It's not just one particular person. But it's the numbers have ended up being used incorrectly. And I want us just to look very carefully at how we rank things like this. How do we go from strongest to weakest base? Because if you get these numbers wrong, you're not going to be able to do it. So how do I do it? Remember that the pKa values that I need to pick up on are always the protonated version of whatever I'm looking at. So if I look at this over here, what I see is a benzene ring and an NH2. It's totally neutral. There are no charges. I need to get the pKa by adding a proton. Now, if I added think about HCl. I'm going to add a proton, always with some strong acid like HCl. If I add a proton to this, where's the proton going to go? It's going to go to the nitrogen. The nitrogen has the lone pairs. And so if it goes to the nitrogen, we're going to get NH3 plus, ammonium. And ammonium, NH3 plus, has a pKa of approximately 11. It's not going to be that for the aniline ammonium. All right. It's not going to be that. It'll be something slightly different. But sort of having sort of roughly what that number will be is absolutely fine. So it's going to be around about 11. And if we look at this, it's the same thing. What happens if we added a strong acid, H+? What are we looking at? Well, the problem is it's this carbon over here, part of that sigma bond to magnesium. That's the most basic part. We're going to put a proton there on this carbon over there. And the pKa of the proton over there is going to be about 43. That's okay. The person wrote 43. I would it's totally fine. Anywhere between 40 and 50 is okay. It's very high. That's all I want is for you to recognize that a carbon, a proton that is on a carbon is going to be between 40 and 50. So that one is fine. Same thing over here. If we add a strong acid to this, this is a O minus. This is a K. If we put a strong acid on this, this O minus is going to get a proton. It's going to become a OH. And an OH, pKa, is 16. That's correct. Looking at this over here, we've got sodium and nitrogen, sodium plus, N minus. So we get NH2 minus. We add a strong acid to that, HCl. Add that acid, we're going to get NH3. And NH3's pKa is approximately 35. So there we have the numbers. And then all we have to do from strongest to weakest base is highest to lowest number. So 1, 2, 3, and 4. Just like that. All right, so hopefully that helped you. It's really important that when you, for those of you who didn't make the 80% on this test, that you can have a look at that. These questions, because these were the ones that really tripped up most people, in order to do a lot better whenever we schedule the next test. All right, thanks.